Yeah, good afternoon. In the last lecture, we have given a general introduction to the nanotechnology and nanoelectronics, and we have projected nanotechnology and the nanoelectronics as the emerging technology, especially beyond 2020, as far as the electronics is concerned. So, one category of device under nanotechnology, we have mentioned that quantum devices, where the quantum effects are going to play a very important role, and that will be the working principle of those devices. So then they are known as quantum devices. Whereas in the case of CMOS devices, as the scaling was going on, we have seen that many of the quantum effects were coming into play, and they were a hindrance to the device behavior. Whereas in quantum devices, this quantum mechanics or quantum mechanical principles will be used for the basic working of the devices. So it is a classic case of joining the enemy and take advantage of it. So this category of devices may be called mesoscopic devices also. What is the meaning of what is mesoscopic? See, their sizes are in the nanoscale, but there will be a cluster of atoms or molecules, and they can go up to measuring micrometers. The lower limit could be in the of individual atoms, and the mesoscopic object, its electronic behavior may be requiring modeling at the level of quantum mechanics. So you have to invoke quantum mechanics to look into the characteristics or the features of the mesoscopic devices. Or we can say the mesoscopic devices are where physics is essentially quantum mechanics, not the quantum mechanics. So unlike in the microscopic devices. The story so far has been, we have seen that CMOS scaling, which was standing on the two legs of, one was the Moore's law and the other was the Dennard's scaling principles. Almost 6 to 7 decades, the microelectronics was standing on these two legs. Then we have seen, due to this intensive scaling, we have seen the emergence of omnipotent and omnipresent electronic revolution or e-revolution. Then if it was in 2006, if it was 65 nanometers, today we are talking of 7 nanometers or even below that. So we had seen a dark silicon era where many of the silicon devices had to, because of the power constraints, it was sitting idle. So we have seen some workaround solutions for that. We have this today. When we talk of microelectronics, we have high performing chips as well as low power chips, where the computational speeds may be compromised. So we are in 2020, and so what next? So it is felt that Moore's law is going to hit the wall because of how far we can go on the scaling. So according to IEEE IRDS map, with the Moore's law may stick around till 2040 or so, with gate-all-around structures and things like that, with the skyscrapers, etc., which we have discussed in the last lecture. So we need to look for alternates to CMOS. So it's like, as I mentioned earlier, the quantum mechanics was the main hindrance in the working of CMOS devices as the scaling was going. So we can take can we take advantage of quantum mechanics? So it's a classic case of joining the enemy rather than fighting it. So what is in store for the future? So if you see, these are some of the possibilities in terms of for example, we may have devices, device architecture, the computational architecture may be changed. There will be cellular array or defect tolerant designs or biologically inspired or the nature inspired computation or the quantum computing. So the computational architecture could be changed because increasingly our thrust will be to improve the performance, not by increasing the number, but our focus is so far, as far as the microelectronics is concerned, our thrust was on scaling. That means put more and more devices into a small silicon area and improve the performance. So the computational performance was improved. But then that is no more a solution. So we need to look beyond scaling, where we can use computational performance using different computational architectures. The number may not be that significant. When I'm talking about the number, it is about the packing density I'm talking of. Because in the traditional microelectronics, that was one thing which was happening. So computational architectures change can help us in performance improvement. Then the logics, the way the logics are implemented, there could be changes in that. You use superconductivity based devices, then quantum based 1D structures, then resonant tunneling, then single electron transistors, then molecular electronics, then QCA and spin transistors. Spin based, rather than using the electric charge of the electron, we can use the spin of the spintronics based devices. So the logics can be changed. The way the logic is implemented is changed. It's not necessarily the traditional switch. So of course, switching action will be there, but the way it is implemented, it is changed. So that is one way. And again, memory forms a very important part of in any computation. So what kind of memories? The phase change memories, floating body DRAMs, then nano field gate devices, like again single electron transistors and insulator resistance change in the system, or molecular electronics can be used for changing the early use of memory with more efficiently and with a higher memory capacity. These principles can be used. These are some of the areas where the work is going on. Then we have seen some of the non-conventional or non-classical CMOS, like where we have enhanced the transport of the carriers by ultra-thin body, single gate, then source drain engineer, because typically we were talking about the strain silicon, then multi-gate field effect transistors. Then we are seeing that we can go for quasi-ballistic or ballistic or quasi-ballistic transport, where we can increase the speed. So these are some of the devices. The research efforts are going on to go beyond 2020, to take electronics beyond 2020. So here we have come across some terms in the last slide. So I briefly discussed about them. Cellular architecture. So in the architecture of the new computation, we can go for the cellular architecture, or it's essentially for parallel processing. It takes multiple architectural design. It gives the programmer the ability to run large number of concurrent threads within a single processor. In this, each cell is a computer node containing thread units. That means they have the memory as well as the communication things are available in that. So here, you get in this architecture, the speed is achieved by exploiting thread level parallelism, which is inherent in many of these applications. So it is essentially a low level programming, and then so this allows the programmer to greatly optimize their code for the platform. It makes difficult to naturally it makes it difficult to develop the software. Yeah, the next term which we have come across is RSX2, that is rapid single flux quantum. This is actually again here the logical information is stored in the form of magnetic flux of quantum and transferred in the form of single flux quantum of voltage pulse. They are essentially implemented using Josephson junctions. Josephson junctions are it's a kind of superconducting device where we have two superconducting layers separated by a thin layer of insulator. So you can the transport can take place between the superconducting layers. It's like essentially like tunneling. If the thickness of the insulating layer is small. So this principle can be used for making RSX2 logics. So this is traditional MOSFET NP channel or N channel MOSFET. Here, then we have a gate in this channel, and then the conduction between source and drain happens through the channel, depending upon and the control is basically the channel conductivity is basically controlled by the gate terminal. So when now looking into the quantum electronics or quantum devices, essentially we talk of the quantum confinement. Confinement, as the name implies, it is the confinement of the carriers, or carriers motion is restricted, or carriers freedom is restricted, or the energy states are restricted. Then we talk of the confinement. So in a typical bulk structure, that is the 3D structure, all carriers act as free carriers, and in all the three directions they are free to move. That is the typical 3D structure, or traditional material, or the bulk properties are decided by that. Then in the case of 2D structures, or they are popularly known as quantum wells, there the carriers are free to move in two directions, but one direction there is restriction. The carrier degree of freedom is restricted. Then we talk of 2D structures or the quantum wells. Then we have if again further, if your confinement is in two directions, or freedom is only in one dimension, then we talk of quantum wires. And if confinement is there in all the three directions, then we talk of quantum dots. So we have this, as well as the quantum effects are concerned, quantum devices are concerned, you have three types of devices. One is quantum well, other one is essentially 2D structures. Then we have 1D, that is quantum wires. CNT is also an example of a quantum wire. A carbon nanotube is essentially a quantum wire. Then you have the quantum dots. Quantum dots are zero-dimensional devices, or since the degree of freedom of electrons is zero, they are known as zero-dimensional devices, and or they are sometimes known as the artificial atoms. So this they are in the quantum well we have seen there are two-dimensional electrons. In the quantum wires, only the electrons are moving in only one dimension, and in quantum dots, zero dimension. confinement is there of the electrons in the all three directions. So, what is the effect of confinement? You can see that this essentially changes energy band structure of the material is changed. Or one quantity which we can talk of as the energy band structure is concerned is the density of states. You can see that in a 3D structure you have a continuous density of states, whereas in the other cases, whether it is 2D or 1D or 0D, you have the density of states is not continuous. There is change, or one is a kind of the step. Kind of in 2D structures you see that, then there are in other cases they have a different. There's a spike in the density of states followed by some very less density of states, and in the case of zero-dimensional devices you see discrete density of states. Now, how can obtain quantum confinement? One can obtain quantum confinement by confinement means we need to restrict the freedom of the carrier. So that means these particles, the electrons, need to be trapped, or their motion has to be restricted. So what we can do is we have, for example, we can get these structures by typically, for example, we can create a physical barrier for these electrons. You have a material with a small band gap and surrounded by a large band gap. Then the carriers will be restricted within that large band gap. In the small gap area, it won't be able to go into the large gap because there will be a barrier existing. So that is essentially the principle used. Essentially we make use of the heterostructures to get the quantum confinement. So the important thing about this is you can, by engineering the confinement, you are changing the energy band structure of the material. By changing the energy band structure of the material, the application for which they can be used also change. For example, earlier days, we were at the mercy of nature to get a particular material for a particular application. An example I would like to mention here is the gallium arsenide. The first generation of optical fibers. Gallium arsenide is one of the most prominent material for making light source, LED or semiconductor lasers. Then we have the optical fibers, and then we have a photon detector or a photodiode which can detect the photons emitted by the gallium arsenide, LED or semiconductor laser. Now the trouble was the optical fiber had the maximum losses corresponding to the wavelength of emission of that gallium arsenide. But we had only gallium arsenide with us during those days. So the lot of efforts have gone. We could not engineer the material that time. But today we can engineer the material according to the application. So for example, we want a particular band gap, we can engineer it and get that particular band gap. So it is extensively used in optical fiber communication. That principle is used in optical fiber communication. You use quantum well lasers, etc. to engineer the band gap, and then we can make devices using that. So this is one. So band gap engineering is possible with this quantum confinement. And again, we have seen that the efficiency especially in semiconductor lasers and semiconductor LEDs. The efficiency increased drastically if we take advantage of the quantum lens or quantum structure. So this is a kind of energy band structure we generally observe in a 3D material. So this is we are familiar with this. We have a conduction band, valence band, separated by the band gap and the continuous energy level. So this is essentially decided by the energy band structure is decided by the host atom and their interatomic distance. So by changing any of these, the interatomic distance or the atoms, we can change the energy band structure. This is the principle because today we are capable of playing with the atoms. So you can keep atoms in a particular position and you can change in principle using atomic force microscope or using tools like that. You can play with the atoms and engineer your band structure. Similarly, by introducing confinement in the form of using heterostructures, you can control the band structure of the material. So this is the idea behind the quantum devices, where you have you can change the energy band structure using you can change the energy band structure by introducing electron confinements in 1, 2, 3 directions. So then which in turn can be used for various applications. So in the next lecture, we will look into some of the devices based like I will be discussing basically about resonant tunneling device and the single electron transistor. Thanks.